Saja or Shahama, have you found the answer for I1? What is I1? Have you got these answers up to this? I1 is 1 ampere and I2 and I3 is minus 0.4. Those who got this answer. Shahama and Saja. Shahama, which one did uh, are you okay the first one, Shahama? Did you get I1 as 1 ampere? And the second one, here, if this capacitor is fully charged, then the current cannot go into this capacitor. Therefore, I2 has to go through this 5 ohm only. Then I2 and I3 are equal. Okay with that? Next, I apply Kirchhoff law for this loop only. In that loop, these two currents are same. So 4 is equal minus, because it is in the opposite direction, minus 10 I dash. I dash is I2 equal I3 equal I dash. So I dash is minus 0.4. Okay. Okay. Check the stored charge. I got this answer. Is it clear here? VC is equal to V1 plus V2. Here, from here to here, we can choose this path or we can go through this path. So here it is VC, here it is V2 plus V1. But V1 is equal 10 into I1. Okay. Here the voltage is in current is in the opposite direction and V1 is in this direction. So you straight away find it. Here also it is like that, but I2 is negative 0.4. So 5 into negative 0.4, you get negative 2. Then final voltage is 8 volt. Is everyone okay with that? Saja, how about you? Okay with the answer? Okay, next topic. Modification of galvanometer. Modification of galvanometer. Galvanometer can be modified galvanometer can be modified to measure large current and voltages. Everyone noted up to this? So let's look how to make a meter using a galvanometer. Already under magnetic field we studied. Now let's look using equations. This resistor is called the shunt resistor. All this together, the galvanometer and the shunt resistor together is the ammeter. So here we have current I, that is to be measured. We have to measure this current I. But a galvanometer only can deflect for small current. For larger current, it might get damaged. So here we have to divide the current as simple I and I minus I. So the idea is simple. This current will divide as simple I and capital I minus I. We know that I is proportional to theta. If we can show that simple I is proportional to capital I, then I can show that capital I is proportional to theta. Don't note this. Did you get the idea behind this principle? We know that I is proportional to theta. If somehow I can show that capital I is proportional to the simple I, then I can tell that capital I is proportional to theta. Therefore, we can use this to measure large current. Is the idea clear? Okay with the idea? So here we can use, I'm going to equate the voltage. V equal IR. If I go through this path, then also V is equal to I minus IR. Both the voltages are same. So let's equate them. If we equate, IR is equal to I minus IR. So IR is equal simple I R plus capital R. Simple R plus capital R. Then we have that capital I is equal I R plus R over simple R. These are constants, therefore I is proportional to simple I. Okay, I is proportional to simple I. Simple I is proportional to theta. Therefore, capital I is proportional to theta. So the deflection is proportional to the larger current, although it is actually measuring the smaller current. Got it? Okay, noted. For an ideal voltmeter, for an ideal ammeter, the potential drop across the ammeter is zero. Next, let's look how to modify this into a voltmeter. So here, this is the voltmeter, okay? This setup, these two resistors and the galvanometer is the voltmeter. So we are going to measure the voltage across this. Need to be measured. These two voltages are same. Okay, so here it's very simple, straightforward. This resistor, we call it as the multiplier. Okay, once you have noted, raise your hand. If you have any doubts, you can ask. So here, actually, the galvanometer is measuring the current, but the current is proportional to this voltage. So voltage is proportional to theta. Okay. Once you have noted, let me know. Raham and Sajja, done. So we can modify this galvanometer to ohm meter also. So ohm meter is used to measure resistance. So here, first we short circuit these two, T1 and T2 is short circuit, and R is adjusted until maximum deflection. Until maximum deflection. This point is 0 ohm. So here we short circuit it initially. We use just a normal wire. And then second, standard resistance values are connected across T1 and T2 and calibrated. When T1 and T2 are not connected, no deflection. R is marked as infinity. Now done. Once you have finished copying, let me know. So not in like other scales. In other scales, maximum deflection will give you the maximum result. But here, the maximum deflection is 0. And the minimum deflection is maximum. Okay. So that is the opposite. So here we don't have a linear scale. So in your page book, write the questions under moving coil meters. Okay, try the questions under moving coil meters. Under voltmeter, under voltmeter write down ideal voltmeter, for ideal voltmeter, the resistance is infinity. Therefore, current through it, current through it is zero. Okay. Finish copying down. Try question number 9. Try question number 9 under moving coil meters. So there we have a galvanometer of internal resistance 200 ohm that will produce a full scale deflection for 5 milliampere. In order to use this as an ammeter which gives full deflection for 10 ampere, so we will use a shunt resistor, right? So this is 10 ampere. Approximate value. We want to find the approximate value. Therefore, just think from 10, if you deduct 0.005, then it won't make much difference, right? So I can straight away consider this almost equal to 10. Agree? So these are then same potential difference. The potential difference across this and across this has to be equal. Therefore, 10R is equal 200 into 5 millivolt. Zero point 0.1 ohm in parallel. Fifth answer. Got this answer? And how about the idea? Clear? Okay, try the remaining questions on the moving coil meters. Let's meet in the next session. Assalamu alaikum.